Welcome to The Explainer. Today we are popping the hood, getting into the engine room of AI to really understand this intense race that's going on to build the next generation of large language models. I mean, it feels like you can't even blink without some company announcing a new, groundbreaking AI model, right? It's faster, it's smarter, it's better than the last one. The pace is just insane. But here's the thing. The real story isn't just about being bigger or getting a higher score on some test. Just look at this quote about a model called DeepSeek V3. It says the performance is right up there with the best of the best, like GPT-4o, but it was trained using 10 to 11 times less computer power. And that, right there, that's the heart of it. The race isn't just about being the smartest anymore. It's about being radically, unbelievably efficient.
Okay, so to really get why efficiency is the new king, we have to talk about this massive wall that basically every AI developer is slamming into. It's called the Great Scaling Problem.
You know, the magic behind these models, the thing that lets them understand context so well, is a process called self-attention. It's how they figure out which words in a sentence relate to all the other words. It's what makes them so powerful. But, and this is a huge but, that power comes with a crazy expensive price tag because the cost to run it grows quadratically. So what does quadratic actually mean in the real world? Well, let's say you double the length of text you give a model. You go from 1 paragraph to 2. The cost doesn't just double, no, it quadruples. And if you 10 times the text, you 100 times the cost. You can see how trying to process something really long, like a book or a big report, just causes the cost in the memory to absolutely explode. And believe me, this is not just some abstract problem on a whiteboard. To train Meta's big Llama 3 model, it took almost 31 million GPU hours. I mean, just try to imagine that. It's an insane amount of energy and money, and it creates this huge bottleneck that really limits who can even afford to build these things.
So you're faced with this giant, expensive wall. What do? Well, the smartest people in AI are basically fighting back on two fronts. The first battlefield is right there, in that core attention engine. They're trying to make it way, way smarter.
So researchers have come up with some incredibly clever hacks to get around this attention problem. We're going to look at 3 of the biggest ones. There's grouped query attention, which is all about sharing. There's multi-head latent attention, which is about compressing things. And then there's sliding window attention, which is kind of a less is more approach.
Now this is where it gets really cool, seeing how each of these methods attacks the same problem. So the standard way, multi-head attention, it's strong, but it's a memory hog. So then you have grouped query attention. This is what Llama uses, and it's a clever trick where a few different parts of the model share the same data, which saves memory. Then there's multi-head latent attention, which goes a step further and actually compresses the data into a smaller version of itself before it stores it, saving a ton of space.
And the third strategy is maybe the most straightforward. It's called sliding window attention, and you'll find it in models like Gemma 3. It basically gives the model tunnel vision. Instead of trying to look at an entire book all at once, it only pays attention to a small chunk of words right around where it's working. It's such a simple idea, but it has a massive effect on cost when you're dealing with long texts.
And this quote just nails the goal here. It's not just about making things cheaper. It's about being cheaper and just as powerful, or maybe even more powerful. This paper is saying that MLA, the compression method, can actually give you more bang for your buck than GQA, the sharing method, for the exact same amount of memory. That's the holy grail. Okay, so that brings us to the second major front in this architecture war. And this strategy, it isn't about just tweaking the engine. No, this is about ripping out the old engine and putting in something totally different, an approach called mixture of expert.
Okay, so think about it like this. A traditional AI model. It's like one doctor trying to be an expert in everything. Cardiology, neurology, the whole deal. It's impossible. A mixture of experts model, or MO, is different. It's like a whole hospital full of specialists. Instead of one giant network trying to know everything, it's got hundreds of smaller, specialized expert networks.
So here's how it works in practice. A piece of information, what we call a token, comes into the system. First, it hits a router, which is basically a super smart traffic cop. The router looks at the token and says, aha, you need to talk to the grammar expert and the history expert. It sends the token only to those 2 specialists. They do their work, their results get combined, and that's the final output. And the difference this makes, it is night and day. In a normal, dense model, every single part of the AI's brain has to turn on and work on every single piece of information. It's brute force. But in an MOE model, only a tiny sliver of the brain activates. This means the model can be absolutely enormous in its total knowledge, but it stays lean, mean, and super fast when it's actually running.
And get this is the key takeaway. It's all about that massive sparsity. Remember DeepSeek V3? It has a mind-blowing 671 billion total parameters. But for any one task, it only actually uses about 37 billion of them. That's around 5%. So you get the knowledge of a gigantic model, but with the speed and cost of a much, much smaller one.
So we've got these smarter attention tricks on one side and this whole mixture of expert structure on the other. So now, let's put it all together and see how the top models are actually using these ideas out in the wild.
If you look at the landscape today, it's really diverse. You've still got the classic transformer, which is a total workhorse. You have MOE models, which are just killing it on efficiency and scale. Then you have other ideas, like RAG, which is like giving the AI an open book test, and even wild new stuff like Mamba that's trying to get rid of attention completely. But here's the real secret sauce. The champions, the top models today, they're not just picking one of these. They're playing mad scientists. They're creating hybrids. DeepSeek V3 combines that huge MOE structure with that super efficient MLA attention. Llama pairs MOE with the very popular GQA. And Gemma 3 focuses on that long text problem with sliding window attention. Everyone is mixing and matching to get that winning edge.
So where is this all going? What does this fierce race for a better, more efficient architecture actually mean for the future of AI? And, for us?
Well, the trend seems to be heading towards systems that are even more dynamic. Look at this rumor about GPT-5. It's described not just as one thing, but as a brain with different modes. So if you ask it a simple question, maybe it uses a quick, low-power mode. But if you give it a really complex problem to solve, it can switch gears and fire up a more powerful, resource-heavy mode. It's AI that allocates its energy on the fly.
In the end game here, the real result of all this brilliant engineering is huge. AI that is cheaper, faster, and more efficient stops being a luxury that only lives in a giant data center. It becomes a utility. It becomes something that can run on your phone, in your car, on everyday devices, unlocking capabilities we haven't even dreamed of yet, and making powerful AI accessible to literally everyone.
So that really leaves us with one big question to think about. As this incredible race keeps unfolding at this breakneck pace, the ultimate winner might not be the model that's the smartest on paper. It might be the one with the most elegant, the most efficient, and the most scalable design. The question is, who's going to build it?